Okay, so this is continuous about from the previous class. And then this one is ethyl methacrylate polymer. This one carbon as oxygen as peak, and then we zoom in this the area. We have three different peaks of the carbon, which is this 1, 2, 3, and oxygen is 1 and 2. So the reason is, if you look at the structures, then the carbon, for example, we have, by the way, we have one bonding rules. The nearby, the subject of the carbon that we want to analyze, and then nearby, you want to look at the nearby atoms what is connected to. So this carbon is carbon, and carbon is carbon connected, but this more important thing is actually electronegative atoms nearby to it. So this is dominant by, not this carbon, dominated by the oxygen from here. This carbon is more serious. This carbonyl group delta minus and delta minus here, so this is more electron diffusion. So I should say type 1, type 2, type 3. This is a all carbon, so this carbon and this carbon are the same type. This carbon and this carbon same type. This carbon, this carbon, this carbon same type. So you have 3 different carbon. So then you have now the highest binding energy show is from the carbon that connecting this carbon connecting to all 2 electron negative the oxygen. This carbon is 1 oxygen connected to it, so probably this one, the shoulder that we see. And these most carbon is actually this carbon. So this is what we want to show. Then the oxygen is 2 different. The oxygen double bond oxygen here, and oxygen connected to carbon and carbon, so you have 2 different carbon. So this is also, the stoichiometry is 1 to 1. So you have 2 different carbons with a stoichiometry 1 to 1. So then 2 different, 1 carbon, 1 oxygen, the second oxygen, stoichiometry 1 to 1. So this is how we analyze it. I will skip several slides because I want to show you general phenomena of this one, for example. So for the carbon, for example, important carbon 1s binding energy positions. Right. So this is the generally we recognizing. So actually it is 284.5 electron volt, but it's okay to say 285 electron volt. This is generally carbon with a nearby carbon binding energy. But now the important thing is the carbon near to some sort of electronegative, the atoms connecting. So nitrogen, oxygen, chloride, and then it's the same oxygen. We have a carbonyl with 1 carbonyl, and then nearby is nitrogen, carbonyl 2 nitrogen, carbonyl oxygen, carbonyl nitrogen, and also the oxygen ester bond. The ester bond, so on and so forth, and 2 fluorine, those kind of things. So see that the trend of the binding energy is increasing as the more electronegative atoms nearby to it. And also the number is important. So you have a carbonyl group 1 versus carbonyl group and oxygen, or carbonyl group and nitrogen. There's a difference. So that's why more electronegative neighborhood that resulting in some binding energy shifted to high binding energy. So this is general. So like a similar that you think about the NMR, for example. In NMR you have we talk about now proton NMR. In proton NMR you have a carbon and proton. If this is like a lipid, just a carbon and carbon chain, you have a protons, then all the chemical shift is from low binding ppm shift, the off-field shifted, down-field shifted, considering if this is kind of situations, then protons you see all the proton NMR peak is nearby off-field shifted, right? And the protons that in the case of the NMR you have some electronegative atoms, and then carbon connected, the proton connected to it, and now we have downfield shifted, downfield shifted more. So you learn about some organic chemistry or analytical chemistry of the NMR. Then general rule is upfield, downfield shifted based on the existence of the electron negative atoms. Same here. Same here. You have this binding, and goes this binding, which is high binding energy, same as NMR. Then you have more electron atoms are nearby too. So we can. I hope that you can better for you to actually understand and memorize even the general trend of this binding energy. Okay, so go back to the different case. Say so let's examine the low resolution and high resolution scan for 3 different polymers. So then now the polyethylene. Polyethylene is basically this N polymers. You have only carbon to carbon connections. So the answer is 285 electron volts. So you have a 285 electron volts, only one carbon, one S from the polyethylene carbon. Now vinyl fluoride, which is now replacing with the fluorine atoms. So the fluorine atoms, you can imagine the periodic table. You have fluorine is right on top. So the electron negative force is actually coming. So that's why this carbon connected to fluorine, and the stoichiometry of this carbon and this carbon with a different environment, which is also carbon to carbon connections. There is no influence from this fluorine for this carbon, because I emphasize only one bond rule. This carbon, one bond here. There's no influence from the fluorine. So it's like 1 to 1. So it's 1 higher binding, 1 285 higher binding energy, 285 higher binding energy, 285. Just 1 to 1. Just 1 to 1. TTFE, this tetrafluoroethylene, all shifted to higher binding energies, or F2, instead of this. So this is the very systematic demonstrations for this actual case. So actually the important thing is there's unavoidable carbon dust in this environment. So you have no matter how you clean the surfaces, there's always little carbon dust is coming down from the ambient conditions. So the actual spectrum is actually no matter how you clean this, and then the carbon from the dust or the ambient condition carbon is contaminated. So this is unavoidable. This case is actually very good cleaning. I should say, generally speaking, you have a relatively higher peak from the hydrocarbon contamination peaks. Okay, so this is actual thing is here. Okay, so so I mentioned this chemical shifted here, and also this is another example. In this case, if you have a gold surfaces, and then gold sulfur binding, which is a system called surface binding. This is called the self-assembled monolayer, SAM. This is one of the famous methods to modify surfaces. For example, you have a gold is a conducting material. For example, this is a sensor electrode, and then you want to immobilize the proteins for glucose sensors, many other sensors. And then you immobilize proteins here, and then glucose oxidase, for example. Then glucose oxidase and got a glucose and get electrons from here. Then they have current generations. So this is kind of configurations of the surface modifications of gold, for example. So anyway, this surface monolayer for the future applications for protein absorption, whatever the cases. So how we analyze the system then? Gold, sulfur. This one is now fluorinated thiol. So this is carbon chains in here. And then you have some gold 4D for F for this. And then you have a fluoride here, and then the carbon and the sulfur 2s and 2p is supposed to be appearing here, but this is only one atom layer, so you have a very small peak. But you can actually prove there is actually peak, because you can actually scan and zoom in this area, and then you can perform one more scan, then you actually clearly see the peaks of the existence of the sulfur 2s and sulfur 2p. Okay, so this is another example. Imagine this is a F8, so you have 8 bonds. So I mentioned that 8 bond is about 8 angstrom. The thickness from here to here is about 8 angstrom, but generally speaking 1 nanometer. So the 1 nanometer, as I mentioned, that the XPS, the thickness resolution is about 20 nanometers. That's why you have gold surface signals coming out of this here. If this chain is much higher in length, that this overall thickness is more than 20 nanometers, then you should not see this gold peak. So this is a good way actually to see when semi-quantitative speaking, that the proteins, what is the thickness of the protein generally speaking on the surfaces. If there's too thick, then you should not see the XPS signals from the substrate. Okay, I mentioned this. So there's some examples in here. Okay, so there's some point. There's a point actually. So this binding energy, for example, when this is a kind of general chemistry classes that we learned about in the periodic table, the binding energy goes higher in these directions to this direction and that directions, right? So this so the binding energy at the comparing at the for example 1s orbitals for this law, then the lowest binding you learn is from the lithium, beryllium, and then this nitrogen these directions, right? So actually, if you learn the XPS for the surfaces from the lithium, pure lithium metal, and whatever carbon, for the graphite, for example, graphene or graphite, nitrogen, for example, nitrogen doped, for example, graphene, or proteins, or boronate, whatever you can bring in surfaces, you take the XPS and XPS, then you actually see the binding energy getting higher and higher as go these directions. Okay. And also I mentioned that this is the total energy you provided. Total energy you provided by the X-ray, and then this is equals to about the binding energy for this 1s electron, and then what we measure is actually kinetic energy, the flying speed of the electrons. So the binding energy plus Ke is, and then plus a little bit, plus as some constant for the instrumentation. Then that is total energy. So that's why the binding energy goes in these directions, but this is an inverse proportional way that this kinetic energy is inverse way directions. Okay, so we talk about the XPS signals and then peak and peak shift, chemical shifted. So let me give you some examples. So we have to remind the tables that I presented before, which is the I give you as a class materials. You can expect, for example, you have some proteins. Say you have H3 plus. Draw like this way. example like this. This is the lysine and serine peptide. Maybe predict. This is I should say peptide. Then predict carbon 1s XPS spectrum. So this is might be the practical examples that I give you. So we focus on just the carbon. So we need to know what type of the carbon we have. So and then maybe CC, CN, CO, CO, carbon and CO, something like this. So maybe, but this is the peptide, so maybe CO, I should say N, or CO, for example. This is might be all the types that we can come up with. So this CC case is maybe I will say the blue one. So this is CC and not this, because C and N is, so that might be the case. And then this is CO, so it's not the case. The CN is not the case. The CO double bonds is not the case. So this is actually the one that we have. So maybe this is C. Number of carbon is 3. CN. Well, actually, there's no truly CN except for this one. Actually, this one is maybe CN that I'll draw like this way. So this is 1. And CO. This one, alright, this one is maybe CO. And there are a lot of actually. This one is CON or COO. It is equivalent, similar in then chemical shift. And this, right? And then CN. This, right? So this is 2. I missed this one actually. This one, so I missed this one, and then that one is might be CC and CN, so that might be the CN. So I'll do number 2. Right. So then, if you think about the actual spectrum, then this is 285, 6, 7, 8, 9. 10. This is actually 290 electron volt. Then this one is number 3. So I'll do 1, 2, and 3 spectrums like maybe like this. And then C and CO is chemically they're about. I don't remember the table number, but it's about here. So then you have, say, about this, like this. And then this is kind of similar in binding energy. And this is kind of separate. So then it goes down. And then you got only 1. This is 2. So I will draw one more about like this. So might be this is kind of a expected spectrums like this. Okay. For this dipeptide case. Maybe also I'll give a different example. Different examples is maybe predict polyethylene glycol. The most popular synthetic polymers that has been used for drugs and cosmetics and many things. PEG. Predict C1 1s carbon 1s XPS spectrum. So the polyethylene glycol's structures is is ethylene, so CH2 and O, that is polymer. Okay. So this might be easier than previous peptide case. So CC, so this is type 1, CO is type 2. So maybe you can expect it like this. So 1 to 1, so like this. If this is the correct answer you think, maybe you're wrong, because actually you draw the actual structures, then it's actually, this is CH2, CH2O, CH2, this is repeating, right? This is polymer. CH2 is repeating, it's very, very many. So actually this is not a different carbon, it's actually the same carbon, because this one is not an asterisk. Because this carbon goes here, so this is CO, this carbon goes here, influenced by the oxygen. So it's not, this is not the right answer. Actually, this is only CO, about 286 electron volt. Peaks are homogeneous, only a single peak that appears. So only like this, single peaks, not the two different. It's only one carbon, one type of the carbon. Okay. So that means you have surfaces. There is a polyethylene glycol on surfaces. Then you take the XPS, which is a lot of frequent cases that surfaces with polyethylene glycol immobilized for many different reasons that I cannot explain for this class. But anyway, so this you XPS, then you think about only homogeneous single peak, that only pH. Okay. This is when you first learn about the XPS, then this is often the cases that often you misunderstand and got wrong answers. So this is right answers. Okay, then maybe I'll continue for analysis of the protein on surfaces for in the case of imaging using the AFM, atomic force microscopy, for next class. Okay, thank you very much.